thanks for watching, and today I would like to talk to you about path independence, which is a very interesting topic that appears both in multivariable calculus, but also I think in algebraic topology and even complex analysis. So this should give you a little bit of a taste of algebraic topology as well. So if you remember, so far we did line integrals, and in general you have to know the line integral depends on the path. So in general, if you take the line integral of f dotted with dr, this depends on the path. On the path C, which means simply, even if you have two curves that have the same start and end points, let's say C and C prime. So suppose you have two curves, C and C prime, with the same starting point and the same end points, like in this figure, then it doesn't mean that the line integral over this path is the same as the line integral over this other path. So in other words, in general, if you take the line integral with respect to C, that's not the same thing as the line integral with respect to C prime. So this is not equal, even though C and C prime have the same start and end points. If you think about this, this makes sense because, for instance, if you want to go from one classroom to the other one, it doesn't always make sense to go straight. Sometimes you can go really run downhill and then quickly run uphill because you have all that momentum. So sometimes it's easier actually to go to the circular path, or if there's some construction at C prime, doesn't always make sense to have go along C prime. But of course, this begs the question, and I'm sure some people are angry for this terminology, so this begs the question, when is the line integral independent of the path? Is this line integral independent of the path? Of the path. In other words, when does it not matter which path you take as long as you have the same starting and end points? And to figure this out, we just need a couple of definitions. So first definition, what does it mean to have a closed path? So C is closed if the start point is the same as the end point. In other words, let me draw you a very nice closed path C, for instance, a circle. See, going this way. Well, it's closed because if you start at this point and you go 2 pi radians this way, you get at the same point you start. On the other hand, something that's not closed is something like that. We have this path C prime, where the start point is not the same as the end point. Now, remember, path dependence or path independence, it's very annoying to check. Namely, in theory, you would have to check that if you have two different paths with the same start and end points, you always get the same answer. For independence, well, it turns out there's a slightly easier test for this that's still hard, but at least much easier than just checking all the possible paths. In other words, it turns out all you need to check is that for every closed path, you get 0. So here's a neat fact. Namely, the line integral is independent of the path if and only if, whenever you take a closed curve, so we start is the end, the line integral is 0. Equals 0 for every closed path C. So, and I will prove this at the end. The proof is absolutely beautiful. So if you want, you can just watch the video and then scroll to the end and you'll see a proof of this. And however, let me just motivate this a little bit. So here's a non-example. Consider, let's say, this closed curve C. But the following vector field F then the question is, again, think you running on a track, like in a circular fashion, and the wind blows sort of along you, sort of in your favor. Then notice, if you actually run on this track, you run faster. So, in other words, the line integral here, if you want the work done of this force on this curve, it's positive. So in particular, it's non-zero. Which means by this test that the line integral is actually dependent on the path. It's dependent on the path. Which is nice. You didn't even need to find two different paths to figure this problem out. You just noticed, well, for this closed loop, the line integral is not zero. All right, and then the question is, so this is already a better test, but still not satisfying because it's still annoying to check that for every closed curve, the line integral is zero. It turns out there's an even easier criterion, which is as follows. So, important fact. Namely, the line integral is independent of path if and only if the vector field F is conservative. In other words, F is the gradient of some function, little f. Which explains yet again why conservative vector fields are nice. And by the way, in case you know some topology, I'm just assuming it's simply connected, everything is nice, so we don't have those weird counterexamples. And this one, I will prove at least one direction. So this direction I just skip, but the way you construct, you do this, if it's independent of path, you explicitly construct an antiderivative. So you kind of say f is the integral of capital F with respect to x, and the other one integral of capital F with respect to y. And because it's independent of path, it gives you the same answer in some sense. But the other thing I wanna prove the other direction because it's a very nice illustration of the test that I just showed. So we want to check that if f is conservative, then the line integral is independent of path. So suppose we do have f is the gradient of some function, And let's check that it's independent of path, which, remember, is equivalent to showing that for every closed C, the integral is 0. So, and therefore, let C be a closed curve. Again, where the start is the end. So this is C. Start equals to the end. Then the line integral of f, well, what does that become? It's the line integral of the gradient of f dotted with the r. But now we have an integral of a derivative, so we can just use the fundamental theorem of calculus, or fundamental theorem of line integrals, which says that this is just f of the endpoint minus f of the starting point. But the start is the end. So in fact, this is 0. So what have we shown? For any closed curve C, the line integral is 0. Therefore, by our other test, the line integral is independent of path. And then you're done. So you see, it's this beautiful thing about this little test, which seems to have nothing to do with anything, but it is true. And just a couple of other remarks. So this thing, the line integral of f dotted with dr, notice it's saying sort of how f moves around C. This is sometimes called the circulation of f around the curve. And what is this saying? Conservative vector fields have 0 circulation. In other words, they are irrotational. So for instance, you can already see that the vector field f like that, it's not conservative because the circulation of f around, let's say, a circle is positive. It's not 0. But for instance, vector fields like that, well, kinda the circulation, if you integrate it around a circle, kinda cancels out and you get 0. So, conservative vector fields, they're not circular, but non-conservative ones are circular. They're rotational. So, in other words, what have we learned? There are many different reasons why conservative vector fields are awesome. First of all, they have an antiderivative. Second of all, the line integral becomes very easy to calculate. Third of all, the line integral is independent of path. And then fourth of all, they're irrotational, so the circulation is 0. And that's more or less all I wanted to talk about, but if you want to stick around, I can quickly prove the neat fact. So here's a neat fact, which I like to remind you, what does that mean? The line integral is independent of path. If and only if the line integral equals 0 for every closed C. Now, how about this one? Suppose the line integral is independent of path. So suppose we have independence of path. And let C be a closed curve. So let's say, suppose C is just a circle or whatever. Since the line, and we want to show that the line integral is 0. Then notice, there are two ways of calculating this line integral. On the one hand, you can just evaluate it along C. On the other hand, there's a much easier path with the same start and end points, which is just a point. So pick some point x0, y0 on this curve, and let C prime be just parameterized by this point. So r of t It's just x naught, y naught. Then, because the integral is independent of path, the original one is the same as the path that does nothing. But then what this is f dotted with r prime of t dt. But r is constant, so the derivative is 0, and f dotted with 0 is 0, so we get 0. In other words, for any closed loop C, the line integral just becomes 0, assuming we have independence of path. The next one, in my opinion, it's even cooler. So suppose that f dotted with dr equals 0 for closed C, and show independence of path. So what does that mean to be independent of path? It means, suppose you have two curves, C and C prime. So let C and C prime be two curves with the same start and end points. And you want to show that the line integral of f with respect to C is the same thing as the line integral of f with respect to C prime. Equals the line integral of C prime, f dotted with dr. Well, the question is, given those two curves, how can we form a closed loop? Because you want to use this fact. Well, just start at this point here and just loop around. So in other words, consider the following path. C double prime, which is just, you start with C, and then, oh shoot, okay. This orientation, okay. So you start with C and C prime, same start and end points. Now, let C double prime be the curve where you start with C, and then you go with C prime, but in the other direction. So in other words, if you want to write this down, so let C double prime just be C followed by minus C prime. You do C, and then you do C prime, but in the other direction. Then notice C double prime is closed. So by assumption, the double integral of f with respect to C double prime is 0. Just using this fact. But then what this is the double integral of f with respect to C followed by minus C prime, f dotted with dr. And if you just break it down, it becomes the line integral of f dotted with dr, and then minus the line integral of f dotted with dr, because for C prime, for C double prime, you're reversing the orientation of C prime. And then if you just follow this loop, if you want, this thing equals to 0. So this is equal 0, and you get the integral of f dotted with dr equals the integral of f dotted with dr, but over the new curve C prime. And therefore the line integral is independent of path. So again, it's a really neat idea. One direction you show it by just having the lazy path that does nothing. This direction you do by having the path that just loops around. Alright, I hope you liked this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.